Participants
Yeah.
have to.
Hello, everyone. This is Vijay. So, if you have any questions on fundamentals of semiconductor devices, you can ask me. Either you can speak or you can type in the chat. Either way. Okay. So, I'll be here for the next around 1 hour or so. Are they here? Sure.
There is no Google form questions.
No problem.
We'll wait for.
Yeah, sure. I'll wait.
Hmm.
If there's any question, they can unmute and ask, right?
Yeah, they can unmute.
Okay, no problem. Sure. No, it's okay. They will unmute and ask. We have two people here. I guess. It showed like 6 participants are waiting in queue, I think. Maybe in on YouTube on this. Oh, 5.
Here is
No, it's okay. They have
Rachi Mohan Verma. He said good morning.
where? Oh, yeah.
Which are-
Yes, please shoot your questions. Okay. It's okay. They will ask. Okay, so I think Rachi Mohan Verma has asked, can you explain how to determine the direction of current? Okay, can you hear me? If you cannot hear me, let me know. Okay, then I'll type the answer. Okay, so to determine the direction of current, it is basically the direction of current is taken to be the direction of the flow of positive charges. So it's opposite to the flow of the direction of the electron. Okay. So for instance, if you have a drift current, you are applying electric field, then the electrons will move opposite to the direction of the electric field. Correct. So the current flow will be in the direction of the applied electric field. So it's that way. Okay. If it is a diffusion current, you have to look at the gradient. In which direction will the electrons, for instance, diffuse, and the direction of current will be the opposite to the direction of movement of electrons. That's how it is taken. So could you hear me, Rachi Mohan Verma? If you are not able to hear me, let me know. I'll type the answers. Okay. Sanchaita Das, yes, it has started. Please ask your questions. Either you can ask by speaking or you can type it here, I guess. There's no one here, right? Nobody's asking it here. So
We'll take message. There will be.
yeah, no problem. I'm checking both of them actually. Okay. I'll keep checking both.
Okay.
So again, I hope you can hear me. If you cannot hear me, please let me know, okay? So Arya has asked, how can we explain energy band of semiconductor? So if you are asking about the concept of energy band of semiconductor, basically each atom has discrete energy levels. When you bring together many atoms together, the energy levels will split and will form many discrete levels, which will merge to form a band. So this is the energy band. In semiconductor, it so happens that you will have two primary bands, where one band is filled with electrons, we call it valence band, and then another band which is not completely filled with electron, we call it conduction band. And the gap between them, energy gap, is the band gap. Okay, so the energy band basically comes from the fact that the discrete energy levels that we talk about for atoms, they split into band when we bring many atoms together to form a crystal. Okay, if you cannot hear me, please let me know. I will be typing the answers then. Krishan Kumar has asked, sir, excellent lecture series. For all my doubt is regarding the scattering from donor and acceptor impurity. Okay, thank you, Krishan Kumar. I hope you can hear me. If you cannot hear me, I will type the answers. Okay, so scattering from donor and acceptor impurity. So whenever a donor or an acceptor atom donates or accepts a carrier, it becomes positively or negatively charged. So for instance, a donor will donate an electron, it will become positively charged. Since it is a positively charged ion now, so what happens is that when an electron is coming or it's traveling in the crystal, the positively charged ion, okay, the positively charged ion will have a Coulombic interaction with the electrons that are moving. So that Coulombic interaction will scatter the electron. It's the Coulombic scattering, okay? Because the ionized impurity has a field around it. It is going to interact with the electrons or holes through Coulomb interaction. Because of that, an incoming electron or a hole will experience a force, it will scatter. It's not a physical hitting and scattering. Like physically, they don't touch each other. It is the field, the Coulombic field, that will attract or repel the electron or hole, and it will scatter them. So that is called this is the scattering from impurities. Okay, and because of that scattering, the electron cannot go as fast as it wants to be. Hence, there is a mobility that is limited by impurity scattering. More the number of donor or acceptor impurity, more will be the scattering, and it will lead to reduced mobility. That's why for higher mobility, the scattering should be lower, which means the donor and acceptor impurity concentration also should be lower. That means the doping should be lower. But you cannot arbitrarily keep decreasing the mobility doping, because for your device, you need a certain amount of doping. Okay. So I have Arya and Krishan Kumar say that they can hear me clearly. So thank you for letting me know. Okay, you can please keep asking your questions. If you have doubts in what I am replying, you can again ask me that you did not understand what I explained. Okay. So there is a question in Zoom or Teams, I guess, Zoom, where Kunal Das has asked, when we draw the periodic potential of atoms, we show the potential only where there are atoms at present as an impulse sort of function. Shouldn't the field exist everywhere? The field vanishes rapidly, actually. Excuse me. The field vanishes rapidly. So the field is shown as not an impulse, but yeah, it's like a rectangular quantum well closer to the atom only. So outside that, the field vanishes rapidly. Okay, that's why we have this, the square wells that are periodically placed for a crystal, and because of that, when the atom comes or electron comes, sorry, it will see the periodic potential only around the atoms, and by solving the periodic potential, we get the Kronig-Penney model, which gives you the band diagram or the band gap. Okay, in general, the field is there, but the field magnitude vanishes. Okay, quickly, I'll switch back to okay, YouTube. So there is no question in YouTube as of now.
Sir, may I ask something?
Yes, please. You are Kunal?
Hello.
Yes. Who is it? What is your name?
Sir, my name is Rachi Mohan Verma.
Rachi Mohan. Yes, please ask me.
Sir, I wanted to ask about The direction of current in PN junction, I'm a little bit confused about it.
In a PN junction, when you apply forward bias, okay, then holes will be injected from P side to N side, correct? So those holes will diffuse in the N side, right? The movement of holes is actually the direction, or the direction of the flow of hole is the direction of the current, okay? And the direction of electron is opposite to the direction of current. That is the basic premise, okay? Do you see my point?
Yes, sir, I got it. One more question, sir. Sir, I want to know about scattering, how it happens, ionized scattering and phonon scattering. Yes,
Correct.
I wanted
So,
details.
right. So whenever an electron, I'm talking about electron, it also applies for holes also. But whenever electrons move in a semiconductor crystal, it will experience scattering. Okay. Just like when you drive a car or a vehicle or a motorbike in the road, if you go too fast, you will hit people, bicycle, trees, etc. Similarly, the electrons will hit some obstacles, that is scattering. It will not physically hit, but the electric field that is set up will scatter it. Okay. So there are different scattering mechanisms. Okay, there are different scattering mechanisms. The most important ones are impurity scattering and phonon scattering. So impurity scattering is basically, I told a little bit back, whenever there are donor and ionized, acceptor ionized impurities, they donate electrons, for instance, or they accept electrons, they become positively charged or negatively charged. So they set up a Coulomb interaction field, and the electrons or holes will interact with that Coulomb field, so that field will scatter them. The electrons that was traveling straight will not be able to travel straight because there's a Coulombic center, it's ionized, so it will penetrate, it will curve the direction of the electron. If the electron is supposed to go straight, but because of the ionized impurity which is giving a Coulombic field, the electron will come and it will scatter and go somewhere else. It will go that way or that way, not physically, but the field will scatter. That is impurity scattering, and that is always there at any given temperature. But if you reduce the doping, for instance, your ionized impurity scattering comes down. The second most important is the phonon scattering. Phonon represents the vibration of atoms. So at any temperature, room temperature, and even low temperature, the atoms in the crystal will keep vibrating. Okay, they will keep vibrating because there is a thermal energy, kT. Because of the thermal energy, the atoms will keep vibrating. Because of the vibration of the atoms, we call them phonon, the unit of vibration of atoms. They can vibrate in different directions. They can vibrate in this direction. They can vibrate in this direction. They can vibrate this direction. They can vibrate this direction. So there are different ways in which they can vibrate. All of them are called phonons, but there are different modes of phonon. There could be acoustic phonon, there could be optical phonon. Okay. So these phonons, when these vibrating atoms also scatter electrons. When the electrons come, they do not physically hit the atom, but the vibration of the atoms will set up a field around it. Okay. A disturbance around it. That will scatter the electron, and that will increase as the temperature increases, because more the temperature, more is the vibration. If you keep going to lower temperature, 10 Kelvin, 5 Kelvin, the vibration becomes very small. So the scattering because of phonons also becomes very small. So phonon scattering and impurity scattering are the two important scatterings that will limit how fast electrons can move. In other words, they can limit the mobility of electron. At higher temperature, phonon scattering will become more stronger. So it will limit. At lower temperature, impurity scattering is more dominant. But impurity scattering overall can be reduced if your doping is low. Apart from this, there are also other scattering mechanisms. For instance, interface roughness scattering. There could be surface, electrons could move close to the surface or interface. There'll be roughness of the surface that can scatter. There is alloy scattering, which basically, if you have an alloy of semiconductor, then the fluctuations of the alloy can scatter. So there are different other scattering mechanisms, but primarily impurity and the phonon scattering are the two most important scattering mechanisms. I hope that could answer your question.
Yes, sir. Thank you.
Okay. So in YouTube Live, I don't see any questions. In Zoom also, I don't see any questions. Okay.
Sir, you were explaining about tunneling. What was that?
Tunneling.
Yes, sir.
Tunneling, actually, the concept of tunneling is from quantum mechanics, and the basics of that same are usually discussed in 10+2, in your 12th standard physics. Basically, what happens is that your electrons, they ideally should not be able to penetrate into a region where the potential barrier exists. But if, for instance, the potential barrier is thin, and out beyond the potential barrier, there is a available energy state, then electron can tunnel through that potential barrier. There is a finite probability that the electron can actually tunnel through a thin barrier and go to the other side. You use the concept of waves there because electrons are wave also, and they have a wave function. So the electron wave function psi, it has a finite probability that the wave function will also exist on the other side of the barrier. So it has tunneled through the thin barrier, which is not possible in a classical picture. For instance, if I take a thin wall and I take a cricket ball or a basketball ball, it will not penetrate through the wall. You have to break the wall to pass it through. But in quantum mechanics, they can actually be penetrating through the wall. Okay, that is called tunneling. And it is important in many aspects because in modern day devices, many of the, when I say potential wall, it could be a layer of material. For instance, silicon dioxide or some material, which is providing a potential confinement. So the electron can actually tunnel through that material and go to the other side of the material. So that is possible, and that has to be taken into account in modern devices. Okay, so it's a very important concept. Many people also use tunneling as a tool, as an advantage. You know, I will use tunneling to actually send the electron to the other side. I will increase the current or whatever. I will try to design a transistor or an LED or whatever by using tunneling to the other side. Okay, so the tunneling concept is very important. It is borrowed from quantum mechanics. It is very much there in modern electronic devices. Okay. So there is a question from Divyanchal Sahu, which asks, what is the difference between threshold voltage of a MOS capacitor and a MOSFET? Right. So ideally, there is no difference per se in the sense that a MOS capacitor does not have the source and drain on both sides. And a MOSFET is basically a MOS capacitor. There is a source and drain on both sides. Okay, that's the only difference. The threshold voltage should only be a function of the doping of the channel, the thickness of the oxide, okay, and the work function of the metal that you're putting in, or polysilicon. It should not be affected by the source and drain, ideally. So it's the same. However, in short channel MOSFET, when the channel length of the gate is very small, the drain will start affecting the performance of the device in terms of threshold voltage. Okay, the threshold voltage may be influenced by the drain voltage, which is not a good thing, but which happens in short channel device. In that case, the threshold voltage of the MOSFET will change, will reduce as the drain voltage is increased. We call it DIBL, drain induced barrier lowering, DIBL. So because of drain induced barrier lowering, the threshold voltage, which should ideally not depend on the drain voltage, now strongly depends on the drain voltage. And that is not a good thing. It happens in short channel device. Okay, otherwise there's no difference per se. Okay. So I hope that answers the question to Divyanchal Sahu. Sonu Yadav asks, I am a little confused about compensated doping and complete ionization. Compensated doping and complete ionization. Oh, I did not get the context of your question, Sonu. But complete ionization means that whatever donors or acceptors you are putting in the semiconductor, they are all completely ionized, which means that one donor is giving one electron, or one acceptor is giving one hole. So if you have 10 to the power 16 donors, you are going to get 10 to the power 16 electrons. That is complete ionization, 100% ion. Compensated doping. Compensated doping is like the term compensation refers to the fact that you have a certain background carrier concentration. You are compensating that, like you are trying to reduce that concentration. You are trying to eat away that or suck away those electrons or holes extra that are there by putting the opposite type of carrier. It may not always be opposite. It can be a mid-gap carrier. It can be a trap or impurity. For instance, you have a semiconductor which has a large carrier concentration of electron. And that has not come because of doping. That has come because of unwanted impurity. Okay. You are not putting any doping, but the semiconductor still has a lot of electrons because of unwanted impurities that somehow came in. So you want to make the semiconductor insulating, almost, you want to reduce that extra electron. How will you do that? You will add some either acceptors, or you will add some traps or mid-gap, acceptor like traps, which will take these extra electrons away. So it's called compensation. You are compensating that extra electrons that was there by putting in some other impurities. So that's called compensated doping. For instance, in gallium nitride semiconductor, which is very widely used nowadays for all LEDs and other things, in gallium nitride, there is a lot of background electron concentration, which is always there. You do not do it. It just comes there. It's called unintentional doping. So to reduce that background electron concentration, which is not good, people put carbon. They put carbon atoms to take these electrons away. To like that one, when I said take these electrons away, I mean the electrons will be taken by the carbon atom. Like the electrons will fall in the carbon atom's energy level and it will get trapped there. So electrons will go away. I mean, not go away. They will be there, but they will be trapped by the carbon's energy levels. A carbon will introduce some energy levels in the band gap. Electrons will go and sit in those energy levels. So the electrons are absorbed by the carbon. In a way, you can think the carbon has compensated the electrons. Okay, so that's called compensated doping. Okay, I hope that is clear. Krishan Kumar is asking, if N equals NC, then EF should be equal to EC. No, it will not be equal because you have to use Joyce-Dickson approximation. Maxwell-Boltzmann approximation will not be correct. You see Fermi-Dirac statistics that we derived. Maxwell-Boltzmann is a special approximation of the Fermi-Dirac. Only when your EF and EC are 3 kT or more separated, then you can use Maxwell-Boltzmann. If it is EC is equal to EF or N equal to NC, at that case, the conduction band and Fermi level are very close. Maybe even they have crossed each other. So the Maxwell-Boltzmann approximation is not true. You have to use a Joyce-Dickson approximation. Okay, you have to use Joyce-Dickson approximation, and you will see that the Fermi level is actually above the conduction band when N equal to NC. Okay, I hope that answers your question, Krishan Kumar. Jeet Sharma says, good morning, sir. Yes, good morning. Mom's Kitchen says, Mom's Kitchen, I don't know this name. Mom's Kitchen says, are we not getting certificate? I don't know that. You have to ask the NPTEL office. I am only an instructor. I teach the semiconductor device fundamentals. Whether you get certificate is something you have to ask the NPTEL office. Okay. Shailender asks, what happens to drift and diffusion current when P and N junction are joined together? When P and N junction are joined together at equilibrium, if you do not apply any voltage, there will be no current. There will be no current. And equilibrium, without shining light, there will be no current. If you're shining light, yeah, then it's like a solar cell. But if you don't shine light, then P and N, when you join, there's no current flowing at all, because electrons and holes, they have a tendency to diffuse to the other side. That diffusion tendency is balanced by the drift. There's a field between the P and N region, the diffusion field. That field will be the opposite to the direction of the diffusion. So that will oppose the diffusion. So drift and diffusion will balance each other. There will be no current at all. Okay, I hope that answers the question, Shailender. Minakshi Chauhan asks, can beta gallium oxide based HEMT have gadolinium oxide as dielectric? In general, for a material to be gate dielectric, the band gap should be large. Otherwise, it should be larger than the channel material. So gadolinium oxide can be a gate dielectric only if its band gap is more than the band gap of beta gallium oxide. I don't know the band gap of gadolinium oxide. Beta gallium oxide is around 4.7, 4.9 electron volt. So if gadolinium oxide has a band gap lower than that, it is not useful. It should have a band gap sufficiently higher, like 6, 7 electron volt. Secondly, its interface with the material, in this case gallium oxide, should be good. If the interface formed has a lot of traps or interface states, then your device will exhibit hysteresis, which means the moment you sweep the current voltage back and forth few times, the device will not perform the same, which is bad for your actual real world application. So whether a material like gadolinium oxide is suitable depends on the band gap, depends on whether it forms a good interface with the dielectric. Okay, and also the band alignment, but I'm not coming to that. These are very important things. So you have to check that. Vinay Kumar asks, my question is effect on semiconductor crystal if both acceptor and donor impurities are doped simultaneously. So if you dope equal number of donor, equal number of electron acceptor, then equal number of hole and equal number of electrons will come, they will compensate each other, they will recombine. There will be no electrons and holes. It will be again like undoped sample, except that there are all kinds of positively charged ions, negatively charged impurities. However, the total number of electron and hole is 0 because you have doped equally. If you dope acceptors more than donor, then there'll be more hole than electron. So all the electrons will be recombining with all the holes, plus there'll be some extra hole. You understand my point? So that's what happens. Vinay Kumar asks, an effect on mobility and number of carrier concentration. Yes, if they are doped equally, and if you assume 100% ionization, then the number of electron and hole will be zero, because equal number of hole and equal number of electrons are there. They all recombine, zero. Mobility will, however, if you are injecting an electron now, that mobility will, however, be low, because you have ionized donors and ionized acceptors in large quantity. They will scatter a lot. So when the electron is traveling, suppose you are putting an electron externally. When the electron is traveling, it will see a lot of electron, a lot of ionized impurity, which will scatter. So the mobility will be much lower than a semiconductor which is not doped at all. Although the undoped semiconductor and this semiconductor will have the same number of free electrons, which is the background carrier concentration, Ni, because extra electrons and holes are gone, if you dope equally. But the mobility will be lower because of ionized impurities carrying. Okay. So that answers the question, I hope, Vinay Kumar and Meenakshi and Chailendra. I'll go to Zoom and quickly see if there's any. So there's a question from Divyanchal Sahu. It's a little deviated question. I'm a final semester MTech student of optoelectronics. Final semester MTech student of optoelectronics, sir. If I top this fundamental of semiconductor devices courses, what are chances of getting PhD under you, sir? I have qualified GATE as well. Okay. Actually, this live session and this course is about fundamental of devices. So I can only answer all the technical questions that you have, all the doubts you have on semiconductor. Whether you can get a PhD with me or an internship with me is something that I cannot discuss here. You have to send me a separate email. Okay. This forum, this course is only for technical questions. Okay. So whatever doubts you have on semiconductor, I can answer here. Other things, I will not be able to answer here. You have to send a separate email. Okay, Divyanchan?
Okay. So may I ask something?
Yes.
Sir, what is the difference between Na minus, and Na, and Nd plus and Nd? In the incomplete ionization, we have seen that.
Yes, incomplete ionization, true. So Na means, I don't know my, Na means the total number of acceptor impurities that you have given. Nd means the total number of donor impurities that you have provided. Na minus it means how many acceptors have actually ionized, how many of them have accepted electron. So for instance, you are putting 100 acceptors, but maybe only 90 of them are accepting electron for some reason, 10 of them are not. So Na is 100, Na minus is 90. Okay, so remaining 10 is not ionized, they have not accepted electron, which means only 90 holes you are going to get. You are not going to get 100 holes. I hope that answers the question. Same thing with Nd plus. I am putting, suppose, 1000 donor atoms, but only 950 of them have ionized and given electron. The rest 50 have not, for whatever reason. So Nd plus is 950. Nd is 1000. And I have only 950 electrons, not 1000 electrons. 50 of them, 50 of the donor atom could not get ionized. Okay, I hope that answers the question. Shailendra is asking, what is the relation between resistance and mobility of electron? Very good. Resistance is actually inverse of the product of mobility and charge. Resistance is the inverse of the product of mobility and charge. Conductance or conductivity is the product of mobility and charge. So the inverse of conductance is the resistance. So that's how it's okay. So if your mobility is low, your resistance will be high. Mobility is high, resistance will be low. Okay. I hope that answers the question, Shailendra. Kusum Koli Day has asked, good morning, sir. Good morning, Kusum Koli. Could you please explain the reason behind change in cut-in voltage with the introduction of trap states? Okay. So ideally, the cut-in voltage of a diode, or we call it the turn-on voltage, it's close to the built-in voltage. Okay, it, in an IV curve, when it rises up, that point is called the turn-on voltage, and it is close to that the built-in voltage, the built-in voltage. Now, if you have traps, okay, when you say traps, it means in the energy band gap, you have certain levels of states that are unwanted, that are traps, maybe because of impurities, maybe because of dangling bonds, interstitial impurities, defects, dislocations. There could be states in the band gap that are traps, in which case the electrons might hop into those traps. Ideally, electrons should only travel in the or transport in the conduction band. That is why the turn-on voltage is equal to your built-in voltage. Correct, because electrons are moving only in conduction band, holes are moving in the valence band. However, if you have traps, electrons can be trapped in them. And then there can be trap-assisted transport. For instance, there can be trap-assisted tunneling, there can be trap-assisted hopping, there can be trap-assisted thermionic emission, we call it Pull-Frankel. There can be different variable trap-assisted transport. So there could be different kind of transport mechanism. Electrons can be in the trap, then they can come out from the trap at different condition, different field, different voltages, different temperatures. So the turn-on voltage will now be affected by the trap. Okay, it can be lower than the turn-on voltage, for instance. Ideally, the turn-on voltage is close to the built-in voltage. But if there are traps in between, the electrons will come out before you reach the turn-on voltage because the traps have emitted the electron. So turn-on voltage might reduce. Okay, so traps have that effect on that. Okay, I hope that answers your question, Kusum Koli. There's a question from Meenakshi. Which software is better, Silvaco or Centaurus? I cannot say that because if I say one is better than the other, I will be championing one software over another software. And the companies can actually question me or sue me, right? On what basis I'm saying that. However, to be very honest, I have not personally used either Silvaco or Centaurus. I have not done simulation myself. Okay, my students do it. My PhD group does it. They do both. They do Silvaco, they do Centaurus. I think they get good results. I mean, it depends on the ease of using. It's like asking which car is better in a way. For the same price, which car is better? It depends on different factors. Some cars will give better mileage, but maybe poorer safety. Some cars may be more comfortable, but poorer mileage. So similarly, different softwares have their different edges and disadvantages. So either you can use, you can get equally good results in both. Meenakshi is also asking, also, how after studying this course, how to proceed with fabrication of devices? Any course or books or suggestion? Fabrication, yes, you can understand the theory and the concepts of fabrication by reading books, but actual experience, you have to go in a clean room and do it. So you have to apply for, I don't know, internship or a student position or project staff. There are many clean rooms now. ISC has a clean room, for instance, and National Nanofabrication Center, IIT Madras, IIT Bombay. There are many of these places have internship opportunities, project staff opportunities. You can touch base with them, you can contact them. If there's opening, you can get into them, you can learn, and then that gives you experience. But a textbook, a good textbook would be, I think I forgot the name of the textbook exactly, but the writer is SMZ. SMZ. Z is SZE. SMZ. Okay. SMZ is a pioneer. He has an epic or a cult textbook on semiconductor devices, but this is a different book on, I think it's called The Physics and Technology of Semiconductor, something. It's a very short book, but it says a lot of useful information on the fabrication, like things like etching, ion implantation, deposition, the diffusion, lithography, everything is there. So that's a good book. Then there's another book by, I think, Campbell. There's a writer called Campbell, and he has this, I forgot the name of the book. It's you can search for Campbell and VLSI fabrication or microelectronic fabrication. You'll see a lot of, there's a lot of good books by Campbell on fabrication also. Okay. So I hope that answers your question, Meenakshi. I'll go back to Zoom again and see.
Sir, I have a question.
Yeah.
Sir, like, why is it the case that electrons and holes have different effective masses, even though like holes are just electron vacancies?
Okay. Holes are just electron vacancy is actually a very simplistic picture. We give that simplistic picture to make it easier to understand about hole. But in reality, holes are very complicated. Hole is not just an absence of electron. It's like the many-body manifestation of the absence of electron. Okay, its quantum mechanics is fairly complicated. Okay, we don't deal with that. So the holes have their own band structure. Electrons have their own band structure. Holes are not just vacancies. These are quasi-particles. They are manifestation of the fact that there is no electron in that gap, in that position. So because of that, they have this own band structure. They have this own, valence band with different branches. So the curvature, as you know probably, the curvature band gives it the effective mass. The holes have these different branches, and they have this own curvature, which gives them a higher effective mass in general than electrons, which have a lower effective mass. Okay, they are not the same. Their effective masses are not the same. Only the charge is the same because hole is an absence of electron. But other than that, they are not same. The holes, the entire quantum mechanics of whole is fairly complicated actually. Okay, we don't deal with that in this course, and so it has its own band structure, its own band theory, and that the effective mass comes because of that. Okay, the curvature of the valence band, okay, in EK diagram. So it's not the same curvature as the curvature of the electron in the top. Okay, so that's the reason why the effective mass of whole is not the same. Okay, qualitatively speaking, if you think about it, a vacancy that moves, instead of electron moving, you have to imagine the vacancy is moving. The vacancy moving in a sea of electron is actually different, qualitatively speaking, than an electron moving among available states. That's the difference because of which you get a mobility difference in electron and hole. Okay, I hope that answers your question. I think your name is Rachi Mohan. So yeah, I hope that answers the question.
Yes, sir. Yes, sir. I wanted to ask what happens when we temperature is low and with phonons and ionized impurity with high temperature.
At higher temperature, phonon scattering will be the dominant scattering mechanism because the atoms will vibrate much more. So the scattering because of that is very strong compared to ionized impurity scattering. However, at very low temperature, the atoms will vibrate very less. So the scattering because of phonon becomes very minimal. So at that time, the ionized impurity scattering becomes more stronger because the electrons will also move slowly now. And in the scattering, when the ionized impurity scattering, the Coulombic field is there, the electrons or holes will spend more time around that Coulombic field, so scatter more. So the ionized impurity scattering becomes more prominent at low temperature, and phonon scattering becomes very prominent at high temperature. That's what happens.
So it means that the other one is that minimal that it is insignificant.
At very low temperature, phonon scattering becomes insignificant. Yes. At close to 0 Kelvin, phonon scattering will almost cease to exist. At very high temperature, few hundred degrees Celsius, for example, your phonon scattering is so high that the contribution from the impurity scattering can be neglected. Almost. So I hope this answers the question. I'm
yes, sir. Thank you.
Yeah. On Zoom, there is one more question.
Sir, is it necessary that the trap state exists at the mid of the depletion region?
Mid of the band gap? No, I mean no. But if you assume that the trap's at the middle of the band gap, then then your analysis and your derivation of equation for Shockley-Hall recombination becomes easier. And in many semiconductor like silicon, for instance, it could be reasonably approximated to be at the middle of the band gap. However, in semiconductors such as gallium nitride, for instance, or gallium arsenide, it need not be at the band gap, the middle of the band gap. It could be closer on the top half or in the bottom half. So then, yeah, you cannot write a very clean analytical equation. You have to do simulation to find out, things like Shockley-Hall recombination, because the position could be at anywhere. For instance, when you add carbon impurities in gallium nitride, it will introduce a trap position which is around 0.9 electron volt above the valence band, which is not mid gap, because the gallium nitride band gap is 3.4, so the middle of the band gap is 1.7 electron, right? But the carbon introduces a trap position at 0.9 electron volt above the valence, so that's how it is there. Okay, so it's not always true. There's some more questions here. Okay. Still here for another maybe 10-15 minutes. So
Sir, when tau becomes a lifetime, what does it mean?
sorry, I couldn't understand you.
When we say that tau is lifetime, what we are referring to?
In the context of Shockley-Hall recombination, or in the context of PN diode?
Shockley Reid Hall.
Lifetime in tau in general represents the average time that the carrier is alive. When I say carrier is alive, I mean before it recombines, say electron, they recombine either with a trap position maybe, or with a hole. If it recombines with a trap, indirectly that's the Shockley-Hall rate. If it recombines with a hole in the band gap, excuse me, the band gap to band gap, we call it the band-to-band combination. So the tau is basically the lifetime. Okay. Now there could be tau due to Shockley-Hall rate, like the electrons will recombine with some trap. It has its own lifetime. Electrons will also recombine with holes in the valence band, that is band-to-band recombination. So there can be two lifetime, tau 1 and tau 2, for instance, and you have to take the harmonic mean of the both to find out the total actual lifetime, the average lifetime. Okay. If one of the factor is more dominant than the other, then you will take only that. For instance, in a direct band gap semiconductor with no impurity, only electrons and holes will recombine band to band, like in an LED, for example. Then your tau is basically the band to band recombination time. Okay. If the material has a lot of defects, then predominantly the tau will be the recombination from electron to the trap, from the hole to the trap level. So that's tau, the average time that it is alive before it combines, microsecond and nanosecond, etc. Okay. Mahesh Singh Yadav asks how to recombine electron and hole. How to recombine electron and hole, as in, like, if you have electrons and holes, they'll always recombine unless you have a field that separates them. Okay. If you take a PN junction, you apply forward voltage, electrons and holes will be injected from the opposite side and they will recombine. Correct? Like an LED, they might recombine in a quantum well and then emit light. If they're traps, electrons and holes can fall into the trap and recombine. So yeah, that recombination is that. I didn't understand the details, but I mean, that's, I guess, answers the question.
Good morning, sir. Sir, how higher band gap is related to the high breakdown voltage and high cutting voltage, sir?
Right. What is your name?
Divanshu Sahu, sir.
Divanshu. Okay. So higher band gap material usually has higher breakdown field and higher breakdown voltage, therefore. Why? Because the way we define breakdown is usually through the avalanche or impact ionization, which means when you apply a sufficiently high electric field, electrons will be accelerated or holes will be accelerated very fast. They will have so much energy, okay, that they will knock off an electron and hole pair from another atom. And which electron and holes that are knocked off starts accelerating, each of them will also create another electron hole pair. So it will cascade and it will avalanche. It's called impact ionization has started. So that's when that happens, your material breaks down. Now, when your band gap of the material is high, okay, when a band gap of the material is high, that it can sustain higher electric field in the sense that electrons and holes that are moving with very high speed or velocity or energy, to knock out another electron hole pair is more difficult because the band gap is large. So the electron hole pair that is knocked out, it has to be knocked out across the band gap. See, the electron holes are there in the valence band, and the electron has to kick them and knock the carrier out. So the electron has to go to conduction band, leaving behind the hole in the valence band. The probability of going to the conduction band becomes less if your band gap is large. If your band gap is very small, then electrons can quickly go to the conduction band, small electric field. Apply small electric field, the electron will accelerate first, it will create an electron pair, it will go to conduction band. The band gap is large. Even if you apply very large field, the electrons will have lower probability of going to the higher band, conduction band. That's why higher band gap, the probability of creating an avalanche or an impact ionization is low in a higher band gap material for a given field than a low band gap material, which means you have to go to a higher field or higher voltage for a higher band gap material to knock them out. That's why higher band gap materials have higher breakdown field. Okay, the impact ionization starts at a later voltage, later electric field, not voltage. Electric field is the critical parameter. Voltage is basically electric field into distance or the thickness of the slab. So we talk electric field is the critical, not the critical voltage. We only talk about critical electric field. Voltage can be anything. You take a material, you take a larger material, voltage will be low or large. So okay, so voltage is not a fundamental property. Electric field is like the more critical property. And so your higher band gap materials will have higher critical field. Okay, so I hope that answers the question. Mahesh Singh Yadav says, sir, suggest books for semiconductor. Semiconductor, there are thousands of books. What topic do you want to study, for instance? If you want to study about basics of semiconductors and compound semiconductor, transistor, not MOSFET, but BJT, field effect transistor. Then one book by Umesh Mishra and Jaspreet Singh. I think it's called Physics and Design of Semiconductor Devices by Umesh Mishra and Jaspreet Singh. It's a very good book. There's a very good book by SMZ, the basics for the physics of semiconductor. SMZ, Z-S-Z-E. Okay, SMZ. There's a book by MS Tyagi. I only know the author's name, book's name I forget. MS Tyagi. His book is also very good for MOSFET, for basic physics, semiconductor devices, etc. Okay, there are many books. You can email me, I'll send you a list. Okay. Dipanjan Mondal. Does the development of superconducting detector fall under solid-state devices discipline or nanotechnology? Oh, I'm sorry. Superconducting detectors, I don't know much. Okay, I'm not an expert there. It probably does not fall so much under solid-state. It will be superconductors. And superconductors come under solid-state devices in a way, but not semiconductor devices. Sorry, they are under solid-state, but they're not semiconductor. I actually don't know about superconductor detectors, so I'm not the right person to answer that. Okay. I hope that answers the question.
Sir, how to visualize the vacuum level that comes after a conduction band in band diagrams?
Vacuum level is basically, if you take vacuum level is the reference with which we define a work function or a electron affinity, like what is the energy you need to kick out or knock out an electron from a crystal completely out. So that's the vacuum level you're talking about. So if you talk, the vacuum level is, for instance, 4 electron volt. The electron affinity is 4 electron volt for a semiconductor. It means from the conduction band, you need 4 electron volt of energy to knock out the electron. Basically, that's what it means. The visualization is in like about 4 electron volt above the conduction band, you have to vacuum level. So that's how it is. I don't know if I got your question correctly.
Yes, sir. I was just asking ki in vacuum layer level, electron where goes, like after conduction band, when it goes to the vacuum level, then where it stays in vacuum level, like how we can interpret vacuum level in a semiconductor, sir?
Vacuum level is not for semiconductor. Vacuum level is for everything. Vacuum level is also there for metals. Vacuum level is the vacuum level. Like you take the electron out of the metal or a semiconductor, insulator, whatever, and electron has come out. So that's the vacuum. Like it's the baseline. It's not for only semiconductor. It's for metals also. It's the energy needed to, the affinity, electron affinity, energy needed to take the electrons out from the crystal. That's all. Vacuum level visualization is in like, if you take a semiconductor, then it's a certain electron affinity away from the conduction band from the conduction band, you add the electron affinity. That is a vacuum level. So that is where you need to take the electron out. That's the energy needed to knock the electron out. Okay. We have around 5, 7 minutes, 6 more minutes.
So what is quasi-neutral region, very small field in N-type or P-type?
Okay. Neutral region is where there's no net charge. So number of free electrons, which are negatively charged, is exactly equal to the number of positively charged ionized donors, which are positive. So the total net charge is 0. It's neutral region. Quasi-neutral region is the same region, but under the application of a bias, for instance, under the application of a voltage, electrons and holes will start flowing. So that neutrality is not strictly held true. The neutrality is not strictly valid. Okay, so there will be some voltage drop. There will be some charge in the background. It's not purely neutral. And the Fermi level, okay, and the conduction band, when I say that it's perfectly neutral, it means the conduction and Fermi level difference is constant. But quasi-neutral, it's actually not. So there's a small drift there. So the electrons and holes will drift in that region. There will be a slight disturbance from the 0 charge condition. There will be some charge happening. That's called quasi-neutral. Okay, the quasi-neutral region comes into picture when you have a high forward bias, for instance, high injection current in a PN diode. A lot of electrons and holes are flowing. A lot of heat is generated. Resistive drop is happening. So the neutral region on the PN side are not strictly neutral. There's a voltage drop there. There's a current flow there. There's the total charge neutrality in that does not hold true. The Fermi level and conduction band or Fermi level and valence band, they're not completely flat. Okay, so that's quasi-neutral region. Hope that answers the question. So can you explain, Kunal Das is asking, can you explain about band tail? The concept of band tail comes in high doping semiconductors. When you have very high doping, very high doping, then your semiconductor bands, the conduction band, valence band are not perfectly smooth. They have like undulation, jaggedness because of too much of electron-electron interaction, too much of many-body interaction. So the density of states that were supposed to exist only above the conduction band or only below the valence band, those density of states can percolate beyond the band edge. Okay. So because of this undulation, and you have the band gap and you have the density of states that are actually coming inside the forbidden gap, you have these small band tails that form. The density of states is not strictly zero as soon as the conduction band starts, because the conduction band is itself not sharp. So that's band tail, okay? Which means within the band gap, the forbidden gap, close to the conduction band, close to the valence band, there can be small amount of density of states there. Electrons can be there. That's the band tail. Okay. I hope that can answer your question. Ladli Bano has asked, does doping change variability? I did not understand your question, Ladli. Does doping change variability? Variability of what? I need to know variability of what to answer the question. Okay, do doping change variability? But variability of what? So if you can tell me that, then I can answer your question. Okay, Ladli. You can speak also if you don't feel. Okay, we have 4 more minutes.
So applying bias means we are giving some electrons or holes to the junction. Does that mean that?
Yes, when I apply a voltage, for instance, to a PN diode, a forward voltage means that I'm injecting holes from the P side and electrons from the N side. Yeah, we are injecting that. Yes.
That is same as doping, not directly, but
doping is basically when in equilibrium, you dope, you put impurity and you change the conductivity. That's all doping. It has nothing to do with the voltage applied. The voltage applied is an external bias that you're applying. It can be applied to a semiconductor which is not even doped, for instance. It's externally you are injecting carriers, externally you're applying a voltage. So Ladli Bano has asked variability of device. Do doping change variability of device? Yes, of course. If you change the doping, the device performance changes. For instance, if you have a PN diode, you keep the P doping same, but you keep increasing the N doping. It will change the performance of the diode. How? Because if your N doping is very high, then the electrons injected from N to P side is much more than the holes injected from P side to N side when you apply forward bias. The terminal voltage will change, the electron current will increase compared to hole current, correct? And your band diagram will change, okay? So, and the leakage also will change. So everything will change. Doping does affect variability of device. Dipanjan Mondal is asking, how would the band structure in a chronic penny model change if the barrier were made thicker? Barrier of what? The barrier of the individual atom. You cannot make them thicker. The barrier is defined by the atoms that you're talking about. For instance, you're taking silicon or you're taking germanium. It has its own material property. It will introduce its own the barrier, the potential. So based on that, your band gap comes. So the chronic penny model is basically the application of the Schrödinger's equation in a periodic potential with this periodic wells, and the periodic wells are dictated by the material. Silicon will have its own wells, energy well. Germanium will have its own well. Gallium arsenide will have its own well. So you cannot arbitrarily change it. For a given material, yes, it's always fixed, correct? You cannot change the crystal structure of silicon just like that. So the chronic penny model is, you can hypothetically solve it, but it's a different material. Okay? You cannot arbitrarily change the crystal structure of silicon, for instance. Ladli Bano is asking, do leakage is significant? You mean to ask if leakage is significant? Leakage is significant in the sense that if you have very highly doped P and N on both sides, then tunneling starts to come in play, and that is a leakage. So yes, leakage is high in a highly doped semiconductor PN diode. Even if you take just a normal N-type material, not a PN diode, just a normal N-type, and its doping is very high, then leakage will be high because the metal that will not be able to form a good Schottky contact. There'll be a lot of tunneling across the barrier, so there'll be a lot of leakage. Yes. Okay. Dibyancha is asking, sir, in future, can photonic IC replace current FinFET IC? I don't know that. I mean, it's photonic IC is not to replace FinFET IC. It is basically to complement and improve the performance of FinFET IC. So photonics people use for certain application there is no photonic equivalent of a transistor, so it's not likely to completely replace. It will help. It will complement. Can you tell little about photonic IC, silicon photonic? I'm sorry, this course is not about photonic IC. You have to ask some other faculty members on that. And photonic book also, I don't know, honestly. Okay, I do not work on silicon photonics. I do not work on photonic ICs. Kusumkol is asking, sir, could you suggest how to learn TCAT simulation in Silvaco in a proper way? Silvaco's simulation TCAT, for instance, will have its own help manual and help file. By looking at that, you can learn. You've gone through the manual, introduction of trap states to specify the degeneracy factor. Is it the hybridization state of the impurity? Yeah, you can think of that. Degeneracy factor is like 2 or 3 or 4. You can start it by putting 2 for electron traps, 4 for hole traps. People have given those in literature. You can look into that. So degeneracy factor is not a very, it will change your device results, but you can take into literature and you can find out what are the degeneracy factors people have done. But look at YouTube, look at many courses like Coursera, Udemy, and etc. They have a lot of these courses. You can, I'm sure you can find out some relevant courses. Okay. Ladli Bano says Zener diode. Yeah, Zener diode is there's a leakage because it's a P and N highly doped, so there's a tunneling current, there's a leakage, high leakage. So yes, Zener diode will have high leakage because, and its breakdown will be very small. Okay, so it is a highly doped on both sides. Yeah. Okay, so I'm told that 11:30 it's 1 hour, so I will have to finish or wrap up today's session. Thank you everyone for your interaction and for your very nice questions. Okay. I really enjoyed the whole session, and I hope to again meet you soon in the next live session. In the meantime, if you do have questions, please feel free to email me. I'll try to answer to your emails as much as possible. Okay. Thank you, everyone.
They can post in Google Form.
Yeah, you can post in Google Form also. You can email me. Okay. Thank you, everyone.
Thank you, sir.
Thanks.
We can